Hello, today I am going to make a presentation about my course project, Adaptive Prediction of Orthogonal Frequency Division Multiplexing System. OFDM schedule is based on FDM schedule, but there are some differences. The first one is that in OFDM system, multiple carriers or subcarriers can carry the information stream together. The subcarriers are orthogonal to each other, so there is no interference between the subcarriers. Secondly, a guard interval is added to each symbol to minimize the uh, channel delay spread and intersymbol interference. There is a picture of the OFDM system in frequency domain to show you how it works. The peaks of the subcarriers are the orthogonally spaced overlapped subcarriers, and the subcarrier nulls correspond to peaks of adjacent subcarriers for zero intercarrier interference. This is an OFDM transmitter structure, in which Sn is the serial stream of binary digits. By inverse multiplexing, there are first demultiplexing into n parallel streams, and each one mapped to a symbol stream, using some modulation constellations, such as quadrature amplitude modulation or the phase shift keys, and so on. Note that the constellation may be different, so some streams can carry a high bit rate than others. An inverse fast Fourier transform is computed on each set of the symbols. Give a set of complex time domain samples. Their samples are then quadrant mixture to passband in the standard way. The real and image components are first converted to the analog domain using digit-to-analog converters, and the analog signals are then used to modulate cosine and sine waves at the carrier frequency, respectively. These signals are then summed to give the transmission signal St and transmit through the air. Then there is the core part of the project, the receiver with the prediction channel with the channel predictor. The upper branch is the conventional OFDM receiver with the equalizer. Hn are estimates of the current channel coefficient that are calculated by the lower branches. The equalized sequences is then passed through a slicer and a decoder to obtain the corrected bits. Then the first algorithm is the RLS algorithm. The recursive least square algorithm is an adaptive filter algorithm that recursively finds the coefficients that minimize weighted linear least square cost function relating to the input signals. The idea of recursive least square filters is to minimize a cost function C by approximately selecting the filter coefficients W or omega, updating the filter as new data arrives. The error signal E is calculated by desired signal D and the filter output D star. The filter coefficient will be updated until the error is smaller than a threshold value, delta Wn, delta W. The second algorithm of the predictor is the normalized least mean square algorithm. The normalized least mean square algorithm is almost the same as the recursive least square algorithm, but it will be trained first before it can get the result. And the weights are used to simulate the results after training. The third algorithm is the kernel least mean square algorithm. Kernel least mean square algorithm are used in kernel adaptive filters. Implement a nonlinear transfer function using kernel methods. In these methods, the signal is mapped into a higher dimension linear feature space, and the nonlinear function is approximated as a sum over kernels, whose domain is the feature space. If this is done in a reproducing kernel Hilbert space, a kernel method can be a universal approximator for a nonlinear function. Then the minimum mean square error estimator is used. This is an estimation method which minimizes the mean square error. Linear minimum mean square error estimators are a popular choice since they are easy to use, easy to calculate, and very versatile. It has given rise to many popular estimators such as Wiener filter and Kalman filter. In the end, this is the result of the simulation. The first one is the best performance of the RLS predictors. The second one is the best performance of minimum mean square error receivers when using the decision-directed OFDM system. That's the part for the project presentation for PPT. And then it's time to show the simulation. The first step of the simulation is set sample frequency, and the scenic prefix period, the symbol period, and the frequency spacing. Then set the simulation parameters such as the length of fast Fourier transform, the length of scenic prefix, and set some metrics to store simulation results. After that, we will generate input symbols and simulate the noise during transmitting. And then we can use the receivers with different predictors to get the result, to get the error of each predictor. And then evaluate the result with the desired symbol, compare the bit error rate, and draw the result figures. The result figures are shown below. The first one is the normalized least mean square receiver's result. And the second one is the kernel least mean square predictor result. The third one is the recursive least square predictor result. As we can see, the third one is the best among three. And then when we use the decision-directed OFDM system, I use the minimum mean square error estimator to process the result. The result is shown in figure 1. As you can see, after the first round, the prediction will be almost correct. Okay, that is all about the presentation and the demo. Thanks for listening.